Hello my dear students, I warmly welcome you to CR Digital Classes. In this lecture, we are going to discuss about properties of elements under homomorphism. Okay, so one of the important theorem. Okay, so let's see the statement of the theorem first of all. So total we have 6 properties of uh, homomorphism of elements. Okay, so in this lecture we are going to discuss first 3 properties. Okay, in the next lecture we are going to discuss another 3 properties. So let's see the statement. If phi mapping capital G to G is a homomorphism. Okay, if phi mapping capital G to G is a homomorphism, then E and E dash are two identity elements in capital G and G dash respectively. Then we have to prove that phi carries the identity of G to the identity of G bar. Okay, that means here in the diagram you have phi is an homomorphism. That phi carries the identity of capital G. Capital G is the domain. Okay, identity of capital G to the identity of G bar means this is the equation format. Phi of E is equal to E bar. I will explain in the proof. Next second condition is pi of a power n is equal to pi of a power n is equal to pi of a whole power n for all small a belongs to capital Z and n belongs to small capital Z. So therefore third condition, if order of A is finite, okay, order of the element in a group is finite, then order of the pi of A divides order of A. What is the pi of A? Homomorphic image of an element. Okay, so A is an element. If you write pi of A, homomorphic image, okay, you have to call it as homomorphic image. Homomorphic image of A. Homomorphic image of A. Order of homomorphic image of A divides the order of the element A. So these are the first 3 statements, first 3 properties of the whole group homomorphism. Okay, so now see the proof. Given pi mapping capital G to G is a homomorphism from the statement. Okay, with the diagrammatic format you can write in this format, capital G and G bar in this format. So mapping is phi mapping. If you take one identity element in capital G, why? Because in the statement they clearly mention that small e and e bar are the two identity elements respectively. Okay, I am taking small e belongs to capital G is an identity element and e bar belongs to capital G bar is another identity element. This e bar has, you can write, image of homomorphic image of the first identity element pi of e. Okay, so therefore where e and e bar are the identity elements of capital G and G bar. So now we are taking the first condition. Okay, pi of e is equal to e bar. Okay, this statement you can also tell in terms of words. Pi carries the identity of capital G to the identity of G bar. Okay, that is in terms of the statement. Since e and e dash is an identity elements in capital G and G bar, so according to the condition, okay, so a into e bar is equal to a into small e. Okay, a into e bar is equal to a into small e. In group theory, we proved one theorem, that is, in a group, identity element is unique. If you take one or two, more than 2 identity elements, at the end of the theorem, we proved that those identity elements are equal. That is, we proved that E is equal to E bar. So then you can say that identity element is unique. Only one identity element exists in any group. Same that condition only. I am multiplying small a on both sides. A into E is equal to A into E bar. For that, now I am applying homomorphic image. These are the elements. Now I am applying that homomorphic image. Okay, multiplying pi on both sides. Pi of A into E bar is equal to pi of A into E. According to the statement of the homomorphism. Why? Because this mapping is homomorphism. Mapping is homomorphism is nothing but clearly that phi satisfying that pi of A into B is equal to pi of A into pi of B. This is the statement of the homomorphism with respect to multiplication, or pi of A plus B is equal to pi of A plus pi of B. This is the statement of the homomorphism with respect to addition. Here we are using with respect to multiplication, so that's why we are using this condition. Pi of A into B is equal to pi of A into pi of E dash, and the second condition is pi of A into pi of E. So therefore, next to this E bar you can write small e into E dash. Okay, so therefore next RHS will be as it is. So by using left cancellation law, LCL, left cancellation law, you can write, you can cancel pi of A on both sides. then you can write E bar is equal to pi of E. Okay, so that is the first proof of the first statement. Pi carries image of capital G to the image of G bar. So that is the first statement. Just we are taking that identity element is unique. From that point we are multiplying small a. After that we are applying homomorphic image. After that applying the homomorphism condition. Then by applying the left cancellation law we are getting the required condition pi of E is equal to E bar. Now we are proving the second condition, that is pi of a power n is equal to pi of a whole power n for all n belongs to integers. Here to prove this condition we are going to use principle of mathematical induction, PMI, principle of mathematical induction. Okay, let a belongs to capital G. A is any element in capital G and image of that a, homomorphic image of that a is equal to pi of a. Pi of a belongs to G bar. That means here you can see clearly, if you take small a is an element in capital G, image of this element will be, okay, so pi of a. This pi of a belongs to G bar. In this format you can denote the diagram. So therefore by PMI, principle of mathematical induction, consider pi of a into a is equal to definition of homomorphism pi of a into a. So pi of a into a means a square. So here you will get pi of a whole square. Okay. So this is the condition. Okay. Given statement is true for n is equal to 2. For n is equal to 2 in case 1 we proved that the given condition. Okay. Now assume that the given statement is true for n is equal to k. Okay. That is pi of a power k is equal to pi of a whole power k. Now where k less than small n. Now for n is equal to k plus 1. So I am taking pi of a power k into a, okay, according to the statement of the homomorphism. So you can write pi of a into k. So pi of a. So therefore now pi of a plus k is equal to. So this value you can write from the case 2. That is the assumption part, you can write that value, or else you can take it as equation star. Okay. So since by star you can write that value. Okay, so pi of a power k is equal to pi of a whole power k into pi of a will be as it is. Bases same, then power should be added. So therefore pi of a whole power k plus 1. So therefore for n is equal to k plus 1 also we proved that LHS is equal to RHS. For 3 cases, for n is equal to 2 and k less than n and n is equal to k plus 1, we proved that the given statement. So therefore by principle of mathematical induction we can say that pi of a power n is equal to pi of a whole power n for all n greater than or is equal to 1. So this is the second statement proof. Okay. Now third statement. This statement is very important for the purpose of short answers also. Not only this one, all 6 statements of this theorem are very important for the purpose of short answers. Okay. So therefore see the third property. Order of pi of a divides order of an element small a. Okay, that is the statement. So given pi mapping G to G bar is a homomorphism, let I am taking that order of an element is equal to small n. First of all I am taking that order of element small a is equal to small n. According to the statement you can write mod a is equal to n. According to the order of an element you can write that value a power n is equal to small e for n belongs to integers. Okay, from the second condition we have this one, pi of a power n is equal to pi of a whole power n. Okay, so now I am writing reverse. Okay, so therefore RHS, okay, pi of a power a whole power n is equal to pi of a power n. So in place of a power n I am writing small e. Why? Because a power n is equal to small e. So according to the first condition, phi of e is equal to e bar. Okay, by condition 1 we are using that pi of e is equal to e bar. So therefore whenever you have pi of a whole power n, pi of a whole power n is equal to e bar, it is also in the form of the order of an element. Then order of pi of a, okay, homomorphic image of that element is also small n. Order of that homomorphic image is also small n. Okay, so then by noun theorem from the group theory, from the subgroup theory, we can say that if a has finite order, a is one element in capital G. For that element, if you have the finite order and a power I is equal to a power j, that means, so if and only if order of a divides I minus j, where small n is the order of a, that order of a divides the subtraction value of the powers of a's. Okay, a power I is equal to a power j. Or else, if order of a power k is equal to small e, okay, that means order of a is equal to k, then order of n divides k. So that means by using these two statements, then you can write that order of pi of a divides order of a in this format. Why? Because order of a we took small n, and order of pi of n also we got small n. So small n divides small n. Okay, so therefore in this format you can divide homomorphic image of an element. Okay, order of homomorphic image of an element divides the order of the element. So this is the third principle of the homomorphism. So I hope you understood this theorem very well. In the next lecture we are coming with remaining three properties. Okay, make a perfect practice, prepare well. For each and every statement you have to represent a diagram, at least one diagram. Okay, that I represented here beginning of the theorem. So you have to draw this diagram in the beginning of the theorem. So you have to explain the theorem through the diagram only. Then only whenever you have the homomorphism condition, these types of diagrams plays key role in the examination. Okay, so until bye, thank you.